In this lecture, I am going to present what are the step-by-step procedure for the analysis of continuous beam by flexibility matrix method. Then I would like to solve one two-span continuous beam problem with one end is fixed and other end is simply supported. These are the different steps used for the analysis of continuous beam by flexibility matrix method or force method. First, determine the degree of static indeterminacy, that is degree of redundancy. Then choose the redundant. Then assign the coordinates 1, 2, 3 and to the redundant. Then remove all the redundant to obtain the release structure. Then determine the displacement in coordinate direction due to given loading in the basic determinant or release structure. Then determine the displacements at the coordinates due to the redundant acting on the release structure. Then compute the net displacement at the coordinates by using the matrix equation delta is equal to delta L plus delta R. Delta is equal to delta L plus del into P. Then apply the condition of compatibility of displacement to compute the redundant. So find out P, that is equal to del inverse delta minus delta L. Then after knowing the redundant, compute the internal member forces by using the equation of statics. So you have to remember, for assembling deflection in release structure and to assemble the flexibility matrix, so use these methods, conjugate beam method or unit load method. Then coming to the problem, analyze the continuous beam shown in figure by flexibility matrix method. This is the two-span continuous beam ABC. The span length AB is 4 meter and span length BC is 3 meter. And on the span AB there is present a uniform distributed load of intensity 60 kN by meter. Then on the span BC there is present a concentrated load at the midpoint of BC. So first find out the degree of static indeterminacy. So the degree of static indeterminacy can be find out, that is the number of reaction components minus the number of equilibrium equations available. So in this case the number of reaction components are 5. So here 3 reaction component, here 1 reaction and here 1 reaction. So the total number of reaction components here 5 and the number of static equilibrium equations available 3. So the degree of static indeterminacy is equal to number of reaction components minus number of equilibrium equations available. So the ds is equal to 5 minus 3, so this is equal to 2. In this case, the two redundants are to be released to make the beam statically determinate. The following alternatives may be used for the release of redundant: MA and MB, MA and RB, RB and RC, MA and RC. These are the different alternatives you can be used for the release of redundant. So in this problem, the moments at A and B, that is MA and MB, are considered as redundant. So the moment at A and the moment at B is considered as a redundant. So first make the structure is release structure. So the release structure comprises two independent simply supported beams AB and BC. After release of the two redundant, so the make the structure is release structure. The release structure comprises of two independent simply supported beams AB and BC. So the coordinates 1 and 2 selected are as shown in figure 2. So these are the two coordinates. This is shown in figure 2. This is the release beam with the assigned coordinate direction 1 and 2. The bending moment diagram in release structure due to external loading is known as the free moment diagram. First draw the free bending moment diagram for span AB. So due to the external loading, what is the maximum bending moment at midpoint of AB? So this is equal to WL square by 8, 60 into 4 square by 8, this is equal to 120 kN meter. Then the free bending moment for span BC, the maximum bending moment at midpoint of BC, this is equal to 100 into 3 by 4, this is equal to 75 kN meter. So the conjugate beam method is used for the determination of displacements due to external load and redundant force. So first find out the displacement due to the external load. The conjugate beam for the release structure has two simply supported beams, A dash B dash and B dash C dash, with M by EI diagram as loads as shown in figure 3. So this is the figure 3. So this is the conjugate beam. The M by EI diagram of the real beam is the loading for the conjugate beam. So here this is that 120 by EI. So this is the loading of the conjugate beam A dash B dash, and 75 by EI. This is the loading of the conjugate beam B dash C dash. So here A dash B dash, this is parabolic loading, and B dash C dash, this is triangular loading. The displacement at coordinate 1 that can be find out in the real beam, delta 1L is equal to the rotation at A in AB is equal to shear at A dash in conjugate beam. You have to find out what is the shear at A dash. So that is equal to the rotation at A in the real beam. So first determine the reaction at A dash and B dash. The loading is symmetrical. The half the load is shared by each reaction. So here first you find out what is the reaction at A dash and B dash. So here the loading is parabolic loading. The reaction at A dash and B dash is equal to the total load divided by 2. So here the total load is equal to 2/3 into base into height, 2/3 into 4 into 120 by EI divided by 2. So this is equal to 160 by EI. So this is the reaction at A dash and B dash. So the shear at A dash in conjugate beam A dash B dash is equal to the reaction at A dash in conjugate beam A dash B dash. So this is equal to the delta 1L is equal to 160 by EI. Then find out the displacement at coordinate 2 due to the external loading. This is equal to rotation at B in AB plus rotation at B in BC. So here you find out displacement here at B dash. So you have to find out what is the reaction at B dash in conjugate beam from AB, and what is the reaction at B dash in conjugate beam from BC span. So shear at B dash in conjugate beam A dash B dash plus shear at B dash in conjugate beam B dash C dash. So shear at B dash in conjugate beam A dash B dash is equal to reaction at B dash in conjugate beam A dash B dash. Shear at B dash in conjugate beam B dash C dash is equal to reaction at B dash in conjugate beam B dash C dash. The reaction at B dash in conjugate beam A dash B dash is equal to the reaction at B dash in conjugate beam A dash B dash is equal to half of this load. So 2/3 into 4 into 120 by EI, 2/3 into 4 into 120 by EI divided by 2. So this is the reaction at B dash in conjugate beam A dash B dash. This is equal to 160 by EI. Similarly, the reaction at B dash in conjugate beam B dash C dash is equal to half into 3 into 75 by EI. Half into 3 into 75 by EI divided by 2. So this is equal to 56.2 by EI. The total displacement at coordinate 2 due to the external loading is equal to 160 by EI plus 56.25 by EI. So this is equal to 216.25 by EI. This is the displacement at coordinate 1 and coordinate 2 due to the external loading. Then find out the displacement due to the redundant. Here you find out the flexibility matrix. Apply unit force in the coordinate direction 1 as shown in figure 4, and then determine delta 11 and delta 21. So first apply the unit force at coordinate 1 and find out delta 11 and delta 21. So this is the release structure with unit force at coordinate 1. So here find out the displacement at coordinate 1 due to the unit force at coordinate 1, and here find out the displacement at coordinate 2 due to the unit force at the coordinate 1. The resulting bending moment diagram divided by EI as shown in figure 5. So this is the loading for the conjugate beam. So here the moment 1 kilonewton meter. So here the moment is 1 and here 0. So this is the triangular shape. The loading of A dash B dash is the triangular shape, and here the M by I is 1 by EI, and here the M by I diagram is 0. So this is the loading for the conjugate beam. So since the conjugate beam is a simply supported beam, so delta 11 is equal to rotation at A in AB is equal to shear at A dash in conjugate beam. So reaction at A dash in conjugate beam is equal to shear at A dash in conjugate beam. So first find out the reaction at A dash by taking moment about B dash. find out the reaction at A dash by taking the moment about B dash. So R A dash into 4 is equal to half into 1 by EI into 4 into 2/3 into 4. 2/3 into 4. So R A dash is equal to 4 by 3I. Similarly, find out delta 11. So delta 11 is equal to R A dash is equal to 4 by 3I. Similarly, find out delta 21. The rotation at B in AP is equal to shear at B dash in conjugate beam. So reaction at B dash in conjugate beam is equal to shear at B dash in conjugate beam. So for reaction at B dash, taking moment about A dash, so RB dash into 4 is equal to half into 1 by EI into 4 into 1 by 3 into 4. RB dash into 4 is equal to half into 4 into 1 by EI into 1 by 3 into 4. So RB dash is equal to 2 by 3EI. So delta 21 is equal to RB dash is equal to 2 by 3EI. Then apply unit force in coordinate direction 2 as shown in figure 6. Here you apply the unit force in coordinate direction 2, then find out what is the displacement due to the unit force at the coordinate 2. So delta 12 is the displacement at 1 coordinate due to unit force at the coordinate 2, and delta 22 is the displacement at coordinate 2 due to the unit force at coordinate 2. So this is the release structure with unit force in coordinate direction 2. So here the moment 1 kilonewton meter and this is 1 kilonewton meter. So here you draw the bending moment diagram, 1 0, this side 1 0, and the M by EI diagram is the loading of the conjugate beam, 1 by EI, the ordinate here 1 by EI, and here 0 0. Delta 12 is equal to rotation at A in AP is equal to shear at A dash in conjugate beam. So reaction at A dash in conjugate beam is equal to shear at A dash in conjugate beam. So for reaction at A dash, taking moment about B dash. So R A dash into 4 is equal to half into 4 into 1 by EI into 1 by 3 into 4. Then R A dash is equal to 2 by 3 EI. So this is equal to delta 12. Similarly, find out delta 22, the rotation at B in AP plus rotation at B in BC. And delta 22 is equal to shear at B dash in conjugate beam A dash B dash plus shear at B dash in conjugate beam B dash C dash. So delta 22 is equal to, so find out what is the reaction at B dash due to this one and due to this one. So the delta 22 is equal to 2 by 3 into half into 4 into 1 by EI plus 2 by 3 into half into 3 into 1 by EI. This is equal to 7 by 3I. So these are the displacement delta 11, delta 22 and delta 21 and delta 22. Then from the consistency condition, the final displacement at the coordinate is equal to delta 1 is equal to 0 and delta 2 is equal to 0, because there is no displacement takes place at the coordinate. Then by using the matrix equation, del P is equal to delta minus delta L. So here you know the flexibility matrix, delta 11, delta 12, delta 21 and delta 22. This is the flexibility matrix, P1, P2. This is the redundant, and this is the displacement at the coordinate. This is 0, and this is the displacement due to the external loading. Then simplify this expression. P1, P2 is equal to 34227 inverse minus 160 minus 216.5. So this is the inverse of the flexibility matrix. Simplify the flexibility matrix, 4227 inverse. So this is the cofactor C11, C12, C21, C22. Then find out the cofactor and find out the adjoint of the given matrix, 7 minus 2 minus 2, 4. And find out the determinant of the given matrix, 4 into 7 minus 2 into 2, 24. Then find out the inverse of the given matrix, del inverse is equal to adjoint of delta by determinant delta, 1 by 24, 7 minus 2 minus 2, 4. Then P1, P2 is equal to the inverse of the flexibility matrix. This is the minus 160 minus 216.5. Then multiply these two matrices, the displacement matrix and the flexibility matrix. Then you get the redundant at coordinate 1 and coordinate 2. P1 is equal to minus 85.875 and P2 is equal to minus 68.250. Then the final support moment is equal to MAB is equal to minus 85.875 kilonewton meter, MBA is equal to plus 68.250 kilonewton meter, MBC is equal to minus 68.250 kilonewton meter, then MCB is equal to 0. Then you know the free bending moment diagram due to external loading. So maximum positive moment for span AB, this is 60 into 4 square by 8, 120 kilonewton meter, and maximum positive moment for span BC 100 into 3 by 4, 75 kilonewton meter. Then this is the direction of the moment. So negative anti-clockwise, and this is positive clockwise, this is negative anti-clockwise. So here this is 85.875 MAB, MBA 68.250 positive, MBC negative 68.250, this is anti-clockwise direction. So this is the direction of the moment. Then after giving the direction of the moment, and draw the bending moment diagram. So here the moment is 85.875, this ordinate 85.875, and this ordinate is 68.250, and here this is 0. Then join these points. This is the negative bending moment diagram. Then due to the UDL on the span AB, so the free bending moment diagram, this is parabolic, and the maximum ordinate is 120 kilonewton meter. Due to the concentrated load at the midpoint of span BC, so here the free bending moment diagram is triangular, and the maximum ordinate is 75 kilonewton meter. And this is the positive bending moment diagram. So here this is negative, this is positive, this is negative, this is positive. This portion is cancelled due to negative positive, and this portion is also cancelled due to negative positive. You can find out what is the maximum positive moment on the span AB here, and maximum positive moment on the span BC. The total moment 120 kilonewton meter, and you have to find out this ordinate. Then after deducting this one, then you can find out what is the maximum positive moment here. Similarly, the total ordinate is 75 kilonewton meter. You have to find out this ordinate. Then after deduct of this ordinate, you can find out what is the maximum positive moment on the span BC. So this is the complete bending moment diagram of the two span continuous beam. Now all are clear. Then how to solve the two span continuous beam? By flexibility matrix method. Then how to draw the bending moment diagram.